So this is a very exciting time for us. We have a colloquium which is of great interest. And I will just introduce the principal speaker, Ken Singer, and then he will introduce the other speakers as the time comes. On the issue of asking questions, it's probably best, because we may be pressed for time, to restrict any questions during the presentations to just ones of clarification rather than general comments or anything. And the question period will be quite open at the end then. And if you could put a question, if you have a pressing question during the presentation, if just put it on the chat opportunity there. Okay, so our opening speaker, Kenneth Singer. He's the Ambrose Swasey Professor of Physics, PhD from University of Pennsylvania. He was a member of technical staff at Bell Labs in the 1980s, and they made him a distinguished member of technical staff. And he was able to parlay that into a faculty position here in physics, for which we're very glad. So that was very nice. He's founded the Center for Materials for Optoelectronic Research and Education, the Moore Center, which is great. He's also something of an entrepreneur and founded Folio Photonics, which was an LLC and now has become an Inc. And so fully incorporated. So I'll turn the session over to Ken, who'll tell us about data science and art.
Great, thank you, Phil. Well, this is a different kind of project for me, for sure. And perhaps this is a different kind of colloquium because we're doing something we can do in the age of Zoom, which is to have a tag team colloquium. So also speaking will be Mike Hinczewski and Betsy Bolman later in the colloquium. So I think the story of this project is maybe a little amusing. Basically, one of my students, Michael McMaster, one day came to me and said he had a new girlfriend who is Lauren Smith, and they wanted to do something together. And so they proposed to me to start a project to use one of the instruments, which I'll tell you about later, in the Moore Center, to try to use it to attribute paintings to particular artists. So within a couple months, my entire group was working on it part-time, and it kind of grew and grew, and all sorts of things grew and grew, and eventually they weren't just boyfriend and girlfriend, they were married, and now they're actually both living in Venice. It's a hard life. Anyway, so we have collaborators in the physics department doing machine learning and also biology. And along the way, Michael enlisted Dean Yoder from the conservation department at the Cleveland Museum of Art, and also a whole class of student painters in Tony Ingressano's class, and you'll see what they did. So the idea is to see if a brush stroke, which creates a texture on the surface of the painting, is able to attribute the artist to the painting. And to do this, we're going to use an imaging method for getting a topographic scan of the whole painting. And then the idea is to use machine learning to see if we can distinguish among the painters. Okay, so what I'm going to say is actually what we're not doing, and this actually, something like this had already appeared in the literature, and basically we have Van Gogh and Seurat here, And if you look closely at the brush strokes, you know, you can tell them apart. This is actually an easy problem. And what we're going to show you is a much harder problem. And we did everything in our power, sometimes on purpose, sometimes on not, to make it really, really hard. So the first thing is, our ambitious goal is to do attribution in a workshop painting. So this is often, well, I'll describe that in a second, but there are a bunch of people who are creating a single painting. And what makes it very hard is they're all trying to imitate the master so that it looks like it wasn't done by a workshop. So that makes it very difficult. And as you'll see, we develop methods that are capable of doing this. And first, though, we're going to try and set up a controlled experiment that will help us to develop the methods that we need to do this. And we're going to use high resolution surface profilometry, which creates XY image on the scale of 10 to 100 microns. So it's very high resolution. And the height that it's able to resolve is tens to hundreds of nanometers. So you will be able to very finely resolve the brush strokes that go into the paint. So shown on the right is an El Greco painting, which I'll describe later, is the one we're going to try to attribute the parts to a workshop. So workshops go back as far as the medieval period, and they're often associated with famous artists who had so many commissions that they really couldn't keep up, and they enlisted people to help them. And it could be they paint one part of it, they get some special people to paint others, and then there are often apprentices that are working on it as well. So at the beginning of this, Michael is basically organized and designed the controlled experiment that's aimed to do this project. And what we wanted to learn is there enough information in these high resolution scans to differentiate between artists? And if so, and you'll see that we are, what exactly in the machine learning is the learning being done on to differentiate and attribute among the artists? And how does this topographical information compare to, say, the photographs that I showed earlier for those two paintings by Van Gogh and Seurat? And then along the way, we're trying to perfect the methods for doing this. So the idea here is to create controls in such a way that we really isolate only the surface texture of the painting. So for example, we fixed all the materials, the brushes, paintings, paint, thinner, canvas, all the same among all the artists who are painting. We got the painters from a Tony's class at the Cleveland Institute of Art. And we tried to remove the subjective information so that only the texture contributes by dividing the paintings into small virtual patches and then doing the learning on the patches. So there were 9 students shown in the lower left. And as you can see, they were each given the same subject, which is a photograph of the lily, and were told to create 3 copies for each student of that painting. And they, as I said, they all use the same canvas, paintbrushes, thinner, so forth. So then we made it even more diabolical, I would say, by choosing 4 out of those 9, and we enlisted Betsy and a couple of her colleagues to use raking light, which is light coming in from the side, to examine the paintings and try and pick 4 that look most alike. And the yellow object in the middle is what raking light looks like the paint. And it actually looks a lot like a grayscale image of one of our scans as well, although this is not quantitative. So after those were selected, then Dean and Michael mounted them on plexiglass boards to support them. And then Ina in the Moore Center used our confocal profilometer to take a scan of a 12 by 15 centimeter area. So this profilometer is basically a scanning confocal microscope, but it uses a broad spectrum and uses the chromatic aberration of the optical system to, as you can see, have the focus at different colors at different heights. And by determining which colors in focus, you're actually measuring the height. And on the right is the full image in a false color of the height across the painting, where the orange is the highest and the blue is the lowest. So the scanning microscope goes in 50 micron increments. It's got very fine 11 micron spatial resolution and 30 nanometer height repeatability. So these are one of the 3 paintings of each of the 4 artists. And you can see they don't look quite very much alike, and it would be quite easy to tell, even for us, who did what, because the other ones are pretty similar. They were told to make them similar. And then on the bottom are the height scans. And you can see, if you looked at these and probably the other ones, it might be rather easy to differentiate. But now, remembering that we would like to use this method for attribution, we really don't want to use the entire painting anyway. And we don't want to have any subjective information. So what we did is cut it into virtual patches. For example, this one's a 200 by 200 pixel patch, centimeter on a side, and use these patches to do the machine learning and attribution. And you can see when you do that, well, first of all, it'll be useful for attributing workshop paintings. It will also create a lot of training data, but also it's really diabolical, because now look at these guys. If I took those labels away, how would you possibly attribute those little patches among the artists? So this makes it apparently would make it very hard, but you can also see that there are a number of length scales in these little patches. So in the one in the upper right, if you look closely, you can see the individual brush strokes. In all of them, you can definitely see the canvas at a larger length scale. And then there are also features that span across the patches. So basically, there's 180 patches for each of the 12 paintings that are being studied. So one of the things that we wanted to do, as I said, is to figure out, when we have the machine learning, what is it actually learning on? What is it about the paintings that make it able to attribute among the various artists. So Sam Schwab did, a student in my lab did empirical mode decomposition. So this is a technique, it's a data-driven technique for sifting the paintings into different bunches of spatial frequency to isolate distinctive modes that are characteristic of certain length scales. So this is going to kind of tell us what length scales are most important in the machine learning. And we're going to be able, once we do the decomposition, to do the machine learning on each of the modes separately or on combinations of the modes. So again, we want to isolate the length scale, and we also think that perhaps maybe removing the canvas might be useful. So why don't we use Fourier filters instead of empirical mode decomposition? So shown here is one of the paintings with the 2D Fourier transform. And the problem with using that is, in order to separate it into modes, you'd have to define boundaries, and how can you do this without bias? And also the Fourier transform has some edge artifacts, which might be a problem. But the EMD actually kind of does this on its own. It's empirical data driven. So to understand it, let's just consider, instead of a two-dimensional image and spatial frequencies, this is actually a time series, for example, of some signal. And you can see there are a lot of wiggles, and they're on different frequency scales. And what the EMD does is it separates them into intrinsic mode functions that go from the highest frequency to the lowest frequency. And when you're all done, when you add them all together, you actually get the original image back. So the way this works is, in this simplification, is you have a signal shown at the top, and then draw a spline between the maxima and minima, those are in red, and then point by point take the mean between the maxima and minima, and then subtract the signal from that. And so that gives you the IMF maybe at the bottom, but then you just do that again and again until it converges and doesn't change much. And that's declared now the first IMF. And you can see that this is the highest frequency signal out of this one, because there's this lower frequency one that goes up and down. So then once you have an IMF, you subtract it from the original signal and start the process until you get the second IMF, and so on. And then there's a residual. When you add them all back up, you get the original signal again. So this is basically the result of one of them. So here's the original profilometry image, and this is the first IMF, and you can see the very fine features. This is the small length scale, high spatial frequency components. And if you look closely, you can see the individual bristles of the brush, and then some other kind of larger structures. The medium feature, as you can see, pretty much, entirely contains the canvas and other features. The blue one, it's really hard to tell, but if you reassemble the whole painting in these colors, what you see is that the blue is actually the actual total brush stroke. So this is what they would learn on in that original work where they're trying to differentiate between Van Gogh and Seurat, but we're not doing that. Okay, so we're going to be doing the machine learning on these. And I believe, oh, no, there's a little more here. Then what we wanted to do is take these mode images and try and assign to them characteristic length scales. So to do that, we took the IMFs and did the Fourier transform on those, and then basically created an average radius for each of the patterns, which is shown here. And you can see they go from higher to lower frequency. And we did this for each artist. And these are the results. So you see at IMF1 is at the highest spatial frequency, but the shortest length scales. And so, and number 2 is at a lower frequency and a longer. And as you can see, you don't really get much more from the higher order modes. So we only did, that's why we only had the 3 images there, the red, which is IMF1, the green IMF2, and then the residual, which is everything. And when you look at this, what you see is that as was obvious from looking at it, that the highest, the IMF1 was at the scale of about 150 microns, which is about the diameter of a bristle. The second mode was somewhere in between, and in fact, it was the periodicity of the canvas. And then the residual is more at the scale of the brush, which we saw when we reconstructed the image from the modes. So now I will turn this over to Mike Hinczewski, who's the Warren E. Rupp Associate Professor of Physics, and he is a biophysical theorist, also doing this as kind of a hobby. So I'll turn it over to Mike.
All right, thank you, Ken. So like Ken mentioned, a lot of this project was conceived and led by students, and in particular, this machine learning part also, we have to give basically primary credit to the students who first came up with these ideas and the methods to try to do this attribution. And that for us, our group, it started with Marcio Dwyer, who was a graduate student in Glenn Starkman's group. He was a cosmologist, and Cecile Adhikari, who was a theoretical biophysicist in my group. And in my own personal case, I also have to give Cecile a lot of credit because he was basically asking me for 4 years to take a look at AI, take a look at these machine learning methods. And I, as a physicist, resisted. I'm like, I don't do black boxes. And finally, he came to me with this project, and it just seemed too fun to pass up. And so really that actually started a kind of change in our own group where we now are applying machine learning methods, not just to this, but to a lot of other like kind of biophysics problems as well. So, you know, Cecile gets props for finally breaking down my resistance. So what I want to do before getting into the results, I just want to give you a very, very brief overview of how machine learning works. So let's say you have a task, it's an image classification task. In this case, it's a cat versus a dog. So you want to be able to have the network look at a picture of a cat and then output the fact that it's a cat. So what you do, this network is essentially in very simple terms, just going to be a series of operations on the pixels of that image. They're going to be a combination of linear and nonlinear operations. And the end result should be an output, which is the correct label for the image. So how do you then train the network? Well, you have to have a huge set of data. So basically images of cats, which are labeled cats, images of dogs, which are labeled dogs. And then you want to essentially change the parameters of that network. So each parameter is known as the weight of a given neuron, and optimize it in such a way that you always get, or with a high probability, you get the correct output given the input. Now, this is in some sense a glorified curve fitting problem. There's a famous saying in physics that if you give me 4 parameters, I can fit an elephant. If you give me 5, I can make its trunk wiggle. And with these networks, though, we're typically talking about 100 million parameters or so, right? So with 100 million parameters, you can do a lot more than making an elephant's trunk wiggle. And that's essentially, and it seems almost crazy to use that many parameters, but what you achieve with it is in many cases just seems purely magical. So let's say you've done that. You've taken the training data, you've now optimized your parameters. So what you do then is you test the network on images of cats or dogs, which is never seen before. So at no point during the training process. And then you check whether you get a good result. And that's what we're going to essentially be we're going to show a lot of the results on basically testing data, which I'll describe in a few slides. Now, these networks that we're using, they're called convolutional neural networks. And so let me just give you a sense of what that means in a little bit more detail. So this is, for example, a case where we have a network that is designed to distinguish handwritten digits. So if you, for example, handwrite an 8, it should output that handwritten digit is indeed an 8. And what these networks do is, so the input image is shown on the bottom, and the next row up is a series of what are known as convolutional layers. So what these are is you take a small matrix, which is kind of a filter that acts on a pixel and its neighbors, and you scan that filter across the entire image. And of course, the parameters of that filter might differ. So every one of the, for example, the 6 images in the row above is a slightly different convolutional filter that's applied to the 8. And what these filters do is essentially they can pick out different features of your image. And then you do a series of subsequent operations. For example, you might downsample the results. You might apply a second convolution to them, and again, downsample. And eventually you map these all onto vectors through several layers until at the very end of the process, you end up with a vector where if you get high output in the 8th place, that corresponds to an output of 8. So even though at some level, this may seem very, very abstract, what the network is essentially doing is breaking down the image into individual features and using those features to make a decision about what's inside, what the original image was. And that's how these convolutional networks work. So in our case, as Ken mentioned, for every single artist, we have 3 paintings. So what we do is we take 2 of those paintings and we're going to be using them for training. And the way we do that is 90% of the patches from those 2 paintings are just going to be used directly to train the weights. And during the training, there's this process called validation, where every so often we check how well the network is doing. So 10% of the patches from those 2 paintings will be used during that validation process. And then there's one whole painting that we never ever show until we're ready to test. And that's going to be our test painting. And we're going to, those are all the remaining patches are going to be part of that testing data set. So we tried out a variety of different techniques, and eventually both Marcio and Cecile graduated, and kind of a new generation of machine learning enthusiasts took over. So Feng Ji, who's a graduate student in theoretical ecology in the biology department, and Gundeep Singh, who's an undergrad physics major, currently now doing a PhD in biophysics in Cornell. And so they're, the structure which they eventually found to work really well is something known as the VGG network, the VGG16. And what we did there is, even though we have maybe hundreds or thousands of patches, this is not a huge amount of data when you're considering that you might have hundreds of millions of parameters that you want to train. So what you do in this case is you actually start with a network that's already been trained on something else. In this particular case, it was trained on millions of images from the internet, cats, dogs, elephants, whatnot. And it already knows how to distinguish features fairly well. Those initial layers of that network do a very good job at kind of extracting the features. And all we did is essentially change the final part of the network, which is the network that's designed to do the classification. So rather than classify into cats, dogs, elephants, it now is designed to classify into which of the 4 artists painted this particular patch. So, and it outputs essentially what you can interpret as a probability vector, where if, for example, 89% of it says that with 89% confidence that the patch came from artist 1, if that's the largest probability that's output, we then say, okay, that patch belonged to artist 1. So that's going to be how we interpret the output. All right, now we have a choice here of how, which input data we can use. We can, of course, in the beginning, we just were feeding in the raw height data to the machine learning, actually getting eventually pretty decent results. But when we decided that, to explore the empirical mode decomposition that Ken mentioned a few slides back, we found that by making the network concentrate on particular spatial features, we can actually improve the results by a bit. And what we eventually found, we tried different combinations of this. So you can fit all the different IMF channels, or you can fit some, selected combo. The one that worked the best overall was if we fed in, because remember these images are, the default format is RGB, so they have 3 different channels. When we were feeding in the height data, we could basically make each channel just the height data. We just made 3 copies of the same thing. But now what we're going to do is we're going to make 2 of those channels the red IMF, so the one that is the smallest spatial frequency. So we're going to make the network really concentrate on that. And then one channel is the medium spatial frequency. And then we found that throwing out all the other information, including the blue channel, which has these large scale features, actually makes the network do better. So in some sense, the blue channel, the large features, were not really relevant to the attribution. So, and then we have one more trick up our sleeve to try to push the accuracy as high as we can possibly do this, in that when we do this training, the entire process of how we find the optimized weights is in some sense a stochastic process. So we get a slightly different answer every time we do it. Part of the way is just the way the algorithm that's designed to search for the weights. Part of the reason is because we choose a different ordering and a different subset of patches every time. So what you'll end up doing is every time you run the training, you'll get a slightly different network. And let's say you do this 100 times, you'll get an ensemble of 100 networks. And this is actually, just as an aside from a physics perspective, really interesting, because these types of ensembles actually have very close parallels to ensembles in statistical physics. It's not quite like an ensemble of like a Boltzmann distribution, an equilibrium, but it actually is closer to something like a non-equilibrium stationary state, and actually satisfies some of the non-equilibrium fluctuation theorems that people have discovered in the last 20 years. And that's something that my group is independently thinking about. In this particular case, though, the ensemble has one nice advantage in that we can basically query each of the networks what the output is, and then average the resulting probability vectors, and then get an overall final artist probability, which it turns out that this method, and I'll show you results later on, does actually push up the accuracy of the prediction, particularly for larger patch sizes. So the final version of the network that we're going to be using then is we're feeding in this empirical mode decomposition data. So 2 red channels, 1 green. We get a copy of 100, ensemble of 100 of these networks. We get the final probability. And now we can, for each individual patch, make an assignment. And what I'm going to show you next is now, these are the 4 paintings that were the test data for each of the artists. If you look at it, in some paintings it's a little bit hard to see, but if you look at so each of these individual patches is color coded. So if the largest probability that was spit out by the network was, for example, for artist 2, we color that patch orange, but the transparency of the patch is related to what confidence it is. So if it's really, opaque orange, that means with, the probability was 95% that it's artist 2. Here, for example, this patch is a little bit lighter orange. That means the probability was maybe 70 or 60% artist 2, but it was still larger than all the other probabilities. So we still can say that that is assigned to artist 2. So what you can see here is that in terms of just absolute errors, just error, which probability was the largest for each patch, for artist 1 and artist 2, out of these 180 patches, there are actually no errors whatsoever in the prediction. For artist 3, we have an error of about 3 out of 180. For artist 4, we have an error of like 9 out of 180. And overall for this thing, it's about 98.3%. And this, in some sense, it's even hard for us to believe that the accuracy eventually reached this point, because if you think about it, if this was a purely random process, if the network was just making a random guess of which patch to assign to which artist, it'll be 25%. And when we first started out on this exploration of machine learning, when we were first trying out our initial machine learning methods, we were getting accuracies in the mid-70s, and we were super happy and patting ourselves in the back about this. And at some point, once we're pushing to like 98%, it becomes almost uncanny and essentially magical. But this is what you can do with 100 million parameters, right? So, of course, this is now just the results of a single patch size, right, for 1 centimeter. And even then, if you think about that, okay, 1 centimeter, think about how small that is, and how you don't have much subjective information there at all. It's crazy that you can achieve that accuracy, but let's see how that depends on the actual patch size. So what I'm showing here, now this is not for the ensemble, this is actually for a single network. So I'll show you the ensemble results a little bit later. This is the mean accuracy as a function of patch size. And so the 1 centimeter result that is about 10 millimeters. So that corresponds right around the middle of the graph. And you can see that there's a sweet spot from roughly, let's say, 5 to 20 millimeters or so, where it's getting accuracies in the high 90s, and then there's a drop-off on either side. And we can actually kind of understand why that drop-off is happening. So if you look at really smaller patches, as you're going down to like 1 millimeter, you actually have a lot more patches to train the network, right, which is good. That's actually a positive thing. Generally, if you give more training data to a network, it can satisfy its task more accurately. But here, because we're getting smaller and smaller patches, there's less kind of, information for attribution in each patch. So despite the fact that you're increasing the training data, you do get an overall decrease in accuracy. Now, still keep in mind that like getting down to 1 millimeter now, so 1 millimeter patches and getting accuracies of 85% is still phenomenal. But once you've been spoiled by, accuracies in the mid-90s, you consider that a little bit disappointing. Now, what happens on the other side? Well, there you actually have the information per patch is actually much greater, right? You even get to see subjective information, more subjective information in each patch. But now, unfortunately, you have far fewer patches for the training. So you do get actually a much steeper drop off. So it seems like the network is actually quite sensitive then to the amount of training data. So there's a sweet spot in the middle where you just have enough patches for training, and each patch is informative, and that's where you get the largest accuracy. You can do this analysis also per artist, right? So here are kind of measures of accuracies for each individual artist. And what you can take from here is that there are certain artists that network actually does much better than others. And the ones that typically are a little bit harder to accurately identify are the ones that are flatter, right? Where the landscape doesn't have as many contrasts in height. And hence it's a little bit harder for the network to distinguish, artists based on texture. But even for those harder artists, which are the blue and green curves, those are artists 3 and 4, you can still see that in this sweet spot range, you still are achieving accuracies in the mid-90s. It just relative to the others, it's a little bit harder to identify. And so the final kind of result aspect that I want to show on in terms of this patch size dependence is what I showed was just the single network results. If we now use the ensemble, we can actually now push the larger patch size where we have far fewer numbers of training data. Now we can push all that higher. So overall then the net result of this is that from about 1 millimeter to tens of millimeters, so we're nearly 2 orders of magnitude in terms of patch size, we're achieving accuracies greater than 80%, which again, like just to emphasize, for us is really, really shocking and surprising, and not something that we were expecting setting out on this project, that the network would be able to work so well regardless of the patch size. So there's one last aspect of the machine learning that I wanted to highlight, and this is the question that eventually came to us that like, okay, so we're doing this entirely on height data, but we could have also equally taken our photographs and broken them up into individual patches and then asked the machine learning to do that and see if you can attribute like 1 millimeter or 1 centimeter sections of the photographs. And indeed, if you took the entire photograph and break it up into pieces, the machine learning actually will do pretty well. But what if you make it a little bit harder, right? Because in some sense, the photo data is extremely rich. Not only does it has data about the color schemes that the artists use, so how exactly the artists would mix their paints and exactly what shades of green or black or yellow they might use. But also the photos have some degree of relief, right? There's some shading, and so there's a little bit of height data as well. So you would think that the photo would be, in some sense, a richer data set, and it's unfair to compare against the height. But let's say you wanted to kind of make this a more interesting comparison. What if we decided to just focus on, to kind of separate out the subjective aspect? So let's say we only trained on the background of the paintings, which are mostly black and green here, and ask the machine learning to predict the attribution of the foreground. Here now, it's a much more challenging task because the photo data, the machine learning might get confused and say, okay, I'm now learning about how to distinguish a bunch of blacks and greens, but now you show me a bunch of yellows and I have no idea what to do. Whereas the hypothesis was that if for the height data, the surface topography, even though the artist is consciously making a different stylistic choice, right? They're going to paint the background differently than they're going to paint the foreground. There is still something inherent and that they basically, it's unconscious almost, that as they touch the brush to the canvas, there's going to be a signature of that regardless of whether they're painting for background or foreground. And that our height method might be able to distinguish that. And so what we did is we took all of our paintings now, we broke them up into background and foreground pieces. There were patches now which were on the border, which we threw out completely, right? So we don't want any patches that are kind of have a mixture of background and foreground. And then we did various tests. So now keep in mind now that if we do this, the number of background patches is going to be very, very small. It's only about 27% of the entire painting. So you have less training data. So overall, for example, you should expect that overall accuracy should decrease. But let's say we do this test. So we train only on the background, and let's do this. And what we did, if we do this in terms of the height data and try to predict the foreground now, so we're testing on the foreground, what we find is that we're getting, our accuracies are now no longer in the mid-90s, we're down to in the mid-70s, right? Because we have far fewer training data. If we try to do the same thing for the photo data, our accuracies are only about 30% or so, which means we're nearly random. So the machine learning gets completely confused by the stylistic difference in the photo data. Like, it's so focused on trying to distinguish the nature of the blacks and greens in the background that it had no clue of how to assign the yellows in the foreground, and basically did almost a random assignment where each patch was randomly assigned to a given artist. Whereas in the height data, there was still information there that it could tease out, even though we had far fewer numbers of patches to train on. And then of course we can do this in the reverse. We can train on the foreground and ask to predict the background. And again, overall now, because there's a lot more training data, both of these accuracies go up by a bit, but we still see this discrepancy where the height data does much better now still than the photo data. So this kind of, for us, this was in some sense the most dramatic result, because it really showed that there is this intrinsic information that's being captured by the height data for attribution, which you can't capture by other means. So with that, I think I'm going to hand it back over to Ken.
Okay, so I'm just going to conclude. We set out our goals at the beginning, and we did in fact determine the optimum conditions. We're transfer learning on ensembles of convolutional neural networks, and that we were able to observe things that are independent of subject. So again, looking at these small patches and randomizing them, you don't really get any information on what the subject of the painting is. It's really just texture and nothing else. And as Mike just described, background versus foreground also makes this approach independent of the subject. And I think, for me, this is the most mind-blowing part of it, is the short length scales. So if you look at that graph that at the bottom here, for 20 pixels, that's a millimeter. Okay, a bristle is about 150 microns. So we're talking about a handful of bristles. And in fact, we did learning down to 5 by 5, and we're still, I believe, in the 70s. So a 5 by 5 is actually 1 or 2 bristles. So the way that the paint is deposited from the bristle onto the canvas evidently is distinct to the artist. And this is just a shocking revelation. So now we have this toolbox, and we want to see if we can apply it in the real world. And this, of course, is much more difficult because these paintings are several hundred years old. They might have dirt on them. They may have had conservation attempts. So it's a much harder problem. But we're going to be collaborating with Factum Arte in Spain. Betsy will describe them a little more. They're the foremost organization at the intersection of art and technology, and they have access to really nice, spectacular artwork. And for us, it will be several of the paintings of the late career of El Greco. And they also have a nice toolbox of custom 3D recording technology. So we're going to be using, or they've already delivered us some scans of a couple of El Greco's paintings using this Lucidic scanner, which is pictured on the right. It's a portable scanner that can be wheeled into the museum, brought up to the painting, but in a non-contact way, optically scans the topographic surface in 48 by 48 tiles. And it gets really high resolution on the order of 100 microns by actually using 2 detectors instead of 1 for triangulation. So triangulation is basically what surveyors use to measure land. And in the lower left is an image of a false colored grayscale image, a grayscale image of the topography of a work. So our next steps, this is one of the paintings that we have from Factum. It's a portrait of Cardinal Tavera, as it is on the right. In the center is what the painting looked like following the Spanish Civil War. You can see that the communists were not too fond of the church. And then Sarah took these 2 photographs and reconstructed a conservation map of the painting on the right. And you can see all the pieces fitting together, except for the 2 that are hatched are missing. And this is actually very interesting for us because now we'll be able to, we have the scan of the picture on the right, and we have the answer that we should expect from machine learning on the right. And we'll be able to test our methods on a real world painting where we know the answer. And once we have this, we can do other things like look at other parts of the painting that might have had other conservation attempts and see what we can discover there. Then after that, we're gonna look at this, which is the Annunciation, the baptism of Christ. And Lauren dug through the art historical literature on the opinion of art historians on which part of the painting was done by who. One is El Greco and then his son, Jorge Manuel. They seem to have always chose Jorge for things that didn't quite look that good, but they might have had it backward actually, because El Greco was quite old at the time and his hand might have been unsteady, and he might have done the ones that don't look so good. But anyways, this is what we're gonna try and determine and create some possible things to study out of this. So now I will turn it over to Betsy. Betsy Bolman is the LCB Smith Professor of Liberal Arts, and she's also chair of the Department of Art History and Art. Betsy?
Thank you, Ken. Thank you, Michael. It's really a pleasure to be here with all of you at this physics colloquium. So Ken and Michael gave you the description of the most high-profile project that we're working on together. But what has been kind of percolating from this collaboration is a whole host of other ways of combining technology, science, and art. And so what I think that we're seeing is potentially the beginnings of a new institute for Case Western Reserve University. And I'm illustrating this on the right with a depiction of a church that I had conserved in Upper Egypt. It dates to the late 5th century, and it has the best preserved coating of paint, of original paint from the Greek, Roman, and early Byzantine worlds. It survived for centuries in the desert. And so this image is created from some of over 600 million data points that Pietro Gaspari, who did a laser scan of the church, created. So he calls this kind of image, it's a cross section of the sanctuary looking north. He calls this kind of image a drawing, although it looks even more accurate than a photograph. So this new institute would involve cultural heritage, the documentation, preservation, and replication of important works of architecture and art, the future of high quality virtual learning, ultimately the transformation of the field of art history. And just so you don't think our goals are modest, I will conclude with the democratization of art. Could you go to the next slide, Ken, please?
Maybe.
There we go. Thank you.
Okay.
So I want to say just a little side word about cultural heritage preservation. Nothing lasts forever, not even the Great Pyramids of Egypt. And so anything that we document is potentially something that we're going to lose at some point, or it's definitely something that we're going to lose at some point. Cultural heritage has been subject of intense political interest in recent years, with the so-called Islamic State blowing up monuments of cultural heritage, following in the footsteps of the Taliban, who blew up monumental Buddhas. And they destroy these monuments of cultural heritage to try to erase other versions of civilization, other kinds of histories, to be able to say that their view of the world was the only view of the world possible, and also to enrage, people in the West who really care a lot about cultural heritage preservation. So historic monuments are never static. The threats include human use, abuse, and assault, as I just described, rising groundwater and other effects of global climate change, which can be absolutely devastating to monuments, insects, I'll say something about termites in a minute, earthquakes, and a host of other forces. And in this view, we're looking at the exterior of the Red Monastery Church in Upper Egypt, the same monument that I showed you an interior view of a minute ago. And there's a red box around the bottom of it. And that shows destruction from rising groundwater. So you can see that the limestone at the very base of the walls there has some shadow and some darker colors. And that's the effect of water destruction on the monument. And the water has attracted termites, and it's possible that the termites might become interested in the straw in the plaster, and then the whole thing will fall apart. So next, please.
Oops. Sorry.
Great. So our projects at present, and these are just a few of them, are that we're hoping to bring together under the umbrella of Art Lab CLE. That's our name, is the optical profilometry project. Of course, that's the jewel in the crown. But also I'm working with HoloLens and the over 600 million data points to create an interactive experience for a class that I'm teaching in the spring on late antique and Byzantine art and architecture. We're also hoping to take advantage of the high quality image recognition work that's being done at Case Western Reserve and ask some big data questions for art history. This has also never been done. A lot of what we're working on has never been done. We also have the potential to do 3D scans and prints of works of art, and I can talk about that later if anyone's interested, but I realize we're actually running out of time. And we're working on non-invasive cross sections of paintings and textiles. That would be super exciting for anyone in the conservation world, in museums. And we're looking at historical data analysis of global ADI results for understanding of display materials in museums. Next, please, Ken. So how are we doing this? Well, I want to just say a word about funding. This project started as all volunteer, and then we got some important support at a key moment from the Provost's office with a Seed Sprint grant. We're always looking for more funding. If anyone out there feels like supporting this, just let us know. We'd be thrilled. But we're also fundamentally doing this because of the collaborative spirit of so many of my colleagues here at Case Western Reserve. And we have, as mentioned, involved the Cleveland Museum of Art in the past, and we have potential future collaborations with them. And then, of course, our collaboration with Factum Arte. Next, please, Ken.
Okay.
So Factum Arte was founded by Adam Lowe, who you see here. He's a polymath and just a simply extraordinary person who has pushed forward the replication of works of art to the point where they're such high quality that you can't tell the difference unless you touch them or turn them over or what have you. And he has a vast amount of 3D scan data. He has an entire, and of course that's digital, but he also has an entire square block in Madrid. It's just really an extraordinary place. And he's collaborating with us. Next, please, Ken. So what happens when the copy is visually indistinguishable from the original? On the left is the original and copy, two photographs of an 18th century painting. And then on the right at the top, we're looking into a facsimile of the tomb of Tutankhamun, which is now actually installed in Egypt and is being used for tourism. So the ability to create something that is as good visually as the original means that you can preserve the actual original. So the tomb of Tutankhamun is now no longer open for people to visit it. They can have actually, it's hard to believe, but the same experience going into the facsimile. And we're at a point where we can not only preserve records of monuments, but share them globally, both physically, as you see in the tomb of Tutankhamun example, and digitally. And we're at a moment similar to the transformative moments of the invention of the printing press and the phonograph, where we're at the threshold of the democratization of art. And I honestly think that what that will do is draw more people to museums, because they'll be able to have an experience, a high quality experience of a work of art that will simply make the original even more alluring. Next slide, please. So this is just the beginning. Case Western Reserve University is poised to lead the transformation of transdisciplinary work between art, science, and technology and research. And also we're poised to redesign the future of visual learning or virtual learning with HoloLens and change the world with the democratization of art. Thank you very much. We're happy to take questions.
Thank you.
How do people give questions? Can they be unmuted, or do they need to write in the, oh, there's a lot of them in the chat, huh?
Yep.
We've been kind of answering questions on the fly in the chat, but if anybody wants to continue kind of the discussion unmuted, feel free to unmute yourself.
Actually, the process would be that you should type if you have a question and we'll unmute you.
Okay, so you have to type your question into the chat. It's not possible to unmute people, is that correct?
We can unmute them as well once we know the questions.
Okay.
So I'm looking now to unmute the first person who asked. All right, so I guess I'm going to call on Jennifer Carter first. Oh, no.
Yes, my question was answered in the chat. I did have another question that I have not posed because it's more of a philosophical. The most interesting part of this project has been the fact that it has touched so many people. It's been really a team effort to make this off the ground. And so in so many cases, I find that graduate students sit in silos of their own work. What do you think the physics department or the art history department has done that have sort of stemmed all of these people to talk to each other about their cool and interesting projects to build collaborations? Do you feel like somebody's done something that the other departments could learn from?
So I'm going to very briefly answer that and maybe turn the floor over to some of the grad students who are actually responsible, who are actually part of the Zoom chat. But my impression is that, like, in some sense, a lot of the people who started this were friends, and in some case, you know, dating each other or part of the same social circle. And so it really began as a conversation, you know, in a social group. And that's the beautiful thing, is that, like, it started with them, and then they were able to rope in their PIs into the process. So it's not like the physics department did anything particularly, you know, special. It's somehow the students, you know, gave birth to this. So I don't know if the students want to give a more detailed explanation.
I'd like to actually jump in with a little something as well for that. So you may or may not know this, that Ken was instrumental in getting the engineering physics program started at Case, and then also in building the Moore Center. Both of those things are really interdisciplinary, transdisciplinary spaces. And I think, I'm going to speak as somebody that's not a physicist, but I do think the physics department does have a really unique capability of being able to interact with other departments. And a lot of our physicists are incredibly collaborative. Harsh, for example, is co-teaching a class in art history right now. So I think there's a built-in branching out, but then the Seed Sprint gave us the opportunity to get started on this work and collaborate further. There was a collaboration event associated with that. And then I think a lot of the people attending the talk came to that event, but also a lot of the students that went to that event ended up working on the project eventually.
Okay, so then there's a question from Nishant Sananaike. Do you want to ask a question? So I've unmuted you, but
I can answer that. So the question is whether we use the high performance computing cluster for training. Yes, we did. So we used actually a combination of the cluster here at Case. Thank you. And also we had individual desktops with GPUs in my lab that we also did some of the training. So it was a combination of both that were used for the whole process.
I have another question.
okay, go ahead.
Yeah. So what kind of Python packages you use? You use TensorFlow or like Keras or like?
Yes. So the final versions, the results that we showed in the presentation, these were all TensorFlow Keras. In the beginning, we used a variety of different things, including, for example, the Mathematica of machine learning. We also used like Gluon for a bit. I mean, there was a variety of different things that we looked at, but like in the end, it was Python, TensorFlow Keras.
Okay, so I have another one question. Sorry. Why did you use VGG over than other pre-trained model? Is there any reason behind that?
We tried actually several. In particular, we compared to ResNet 50. ResNet 50 was a bit bigger, even with even more parameters. So we found the results not improve that much, depending when we switched between. So we chose VGG essentially because it's in that field of image classification models, it's fairly lightweight. So that was more of us, so the training was quicker. But we did compare to other models and we got similar results.
Yeah, thank you.
All right, so Annette, do you want to ask your question?
Yes, I was just curious. Could you use the same kind of thing for like forensics for like signatures or perhaps historical documents as to whether or not signature is by the same person instead of using like topography, maybe using like intensity of ink, brush strokes, the same kind of process?
I think we can. In fact, Mike McMaster, who's here on the Zoom, is actually, I think, beginning to look at, there's a historical map and looking at, doing potentially machine learning on that, where we're looking at, texture and ink on the sort of, I don't know, Mike, you wanted to.
Yeah, I can hop in. Yeah, I'm tuning in from Venice, where I'm here at the a building hosted, it's a project called Archive, and there's this entire project called the European Time Machine, where they're trying to not only record all of the physical architecture of the many cities that are endangered and eventually all of Europe, but also tie those buildings to documents that are associated with them and have names of people that lived in them, for example. And the way that they're trying to do this mass digitization is using very similar training networks in a different way than we are, specifically to look at different types of handwriting, figure out what the handwriting says and categorize it. And then there's other efforts that are being used to look at historical documents and translate them, figure out who the author is. I've seen a few studies of people who are using it to look at the way the brush strokes are created and try to assign these to specific tools, and then use that to look at the way that language and specifically writing and tooling of writing transferred in early history and how language grew that way. Yeah, Venice, Italy. Just saw Dr. Strandi's message. But yeah, so this is being used fairly widely, and it's all similar technology, just not implemented the way that we are using it.
Okay, so there's a question from Max McMillan. Do you want to ask your question now?
Yeah, hello. I'm actually Jace. I'm another CIA painting student.
Oh, okay.
I'm wondering if there's any plans to use this technology for like generating art, or like could this research be used to develop a generative model, or like is there anything that like what are you guys gonna do with it?
Yeah,
I just want to jump in, Michael, and just say that Factum Arte has actually recreated works of art that were from fragments of almost destroyed, like an almost destroyed Monet painting. The blackened fragments of it were found a few years ago, and it had been burned in the 60s, and it had never been photographed in color. And Adam was able to use the data that he had to put the painting back together and make some very well-informed guesses. Sorry, Michael.
Yeah, I mean, yeah, that's actually a great answer, because in some sense, like filling in, missing patches is a really important, for example, aspect. We don't consider that as a creative thing, right? But it's a really important aspect to art conservation. And it wasn't quite the goal of this, but the relationship, there's a close relationship between types of convolutional networks that we're using and other types of networks that can be used, that called generative networks, that can be used to actually, once we learn essentially the signature, they can be used to create essentially fake. If you've heard the term deep fakes and things like this, you can more or less try to fake that signature in another context. What's interesting here is, though, of course, we're learning how to fake the signature in that sense over really small patches, not necessarily over entire subject areas. So yeah, what kind of art would result from trying to use these to generate things? It's something that we would have to see, but it would be maybe an interesting exercise.
So, I mean, one question from our work is, what exactly is making each painter distinctive? So this could be an intentional stylistic aspect, or probably is likely some kind of physiological aspect. So it might be possible, for example, to create an artificial hand that could be programmed from the learning that would deposit paint in the same manner. That would essentially, it would be a forgery on the scale of 100 microns is what it would be. And that actually might be possible.
So there's a question from Mike M. Do you want to ask that?
Yeah, I guess I was just curious how much a forger that had access to this technology could improve their forgeries. I mean, I'm just wondering how much of this is in the control of the artist and their brushstrokes, and how much is just inherent in their, there's only so much that they can do.
So, forgeries are usually discovered by chemical analysis and things like that. So we probably don't think this is going to be all that useful for discovering forgeries.
Perhaps I can jump in here and just suggest that we have one more question as part of the formal colloquium, and then we can stop the recording and turn over to an more informal discussion with any of those who would like to stay behind and ask further questions. So shall we take one more? Is there one more question?
Well, I'd be happy to ask that question. So I think it was partially answered, Mike, in the chats, but you plan to do some further work with the students. I was wondering what kinds of issues you want to explore with that additional work.
Yeah, so if what we're claiming is true, right, that essentially there's some inherent thing about the brush stroke signatures independent of subject matter, it should now work that if we ask the same 4 student painters to go and now do paintings, you know, of some totally different subject, that we should still be able to distinguish patches from those paintings using the existing network. That's something that would be a really interesting experiment to do. And it's just a question of getting the whole, you know, everybody together in the middle of this kind of pandemic situation. So it's not something that we were able to have been able to do this year, but we're thinking about that as one potential, you know, future avenue, is to now check, you know, that this, you know, that this hypothesis that it's basically subject independent actually pans out.
Okay, so this has been, I think, an amazingly successful colloquium, fascinating subject, and moving so fast. I think we should have an annual colloquium on the same topic at the speed you guys are going. So thanks once again. Virtual applause to everybody who has contributed, and we'll terminate the recording now. And